resource adequacy topic. As I mentioned, Elizabeth has really been a leader in this space, and so I'll pass it off to you.
Great. Thank you, Ben. I am pretty excited to kind of bring this topic. This kind of started earlier in the year in discussions about resource adequacy and kind of understanding all the different resource adequacy topics, how all of this fits together, all the different regional analysis and utility analysis that happens around resource adequacy. And really the intent is this is kind of a starting point for the series. And the intent with the series is kind of bring a learning resource to help the understanding of what are these metrics, how do they fit together, the different modeling techniques, and their approaches to resource adequacy. And then at the end, how does this fit into our modeling techniques for our IRPs, system optimization, and our capacity expansion modeling, and these different aspects we need to think about for making sure there is enough resources. And so really, I'm very excited that Dor was able to come for the first series and really kind of do this introduction into resource adequacy. Dor is with the Northwest Power and Conservation Council, and he is the chair of the Resource Adequacy Advisory Committee at the council. And so he really leads this effort for the work that the Northwest Council is doing for their power plan. And so I'm actually pretty excited he's able to talk to you and about the different topics and just a little bit of kind of logistics of today's meeting. Since this is the main topic for the meeting, we are going to take a little short break in the middle. So, we can stop and take a break. And also, his intent is to have discussions. It's a learning opportunity to understand. And so if you have questions, just kind of raise your digital hand or just put it in the chat and we'll make sure to monitor so we can get questions answered and just really have a discussion on this. And so I'm really excited to introduce Dor for this meeting.
Elizabeth, really excited to be here today, and really PNUCC for extending the invitation and preparing these sessions. I'm going to slide the webinar here, so I might ping pong back and forth. Apologies. I can also close the camera if that is distracting, but I will just share the screen. We test drove this earlier. So thumbs up, presenter mode. Okay, perfect. So as I said, very excited to be here today. Many of you know when I get excited, I talk fast, so I will try to rein in my excitement a little more. But I really do love talking about these topics. The agenda you just saw for the series, I think, is very well planned, and a lot of the words you saw on that screen will be mentioned today, but we will spend more time on the metrics themselves, how do we think about them, the bigger picture, but some of these would really lead into the second and third topics. Just make sure I can click. Okay, it moved, just making sure. Okay, thank you. We'll talk about 4 things, not in equally weighted time. Most of what we'll do today will be about defining risk and what RA metrics measure, as well as the actual metrics, and we'll go through the examples. I think that's where we'll have a good time for a break, and then we will transition to how do we conduct adequacy assessments, really the 2 types of assessments that we often talk about, and then what comes after the assessment. I do encourage questions. Elisa and Elizabeth, thank you for making sure I don't miss any. And really, I will foreshadow, there might be some repetitions or circularity. These are topics that we might back and forth bounce throughout the presentation. There won't be a lot of definitions today. There will be some math because math is fun. It could be simplified equations, but really it's important to understand from the get-go, when we're talking about resource adequacy, there are several definitions out there. They might vary by a word here, a word there. But at its core, it's a measure of the ability of a power system, and this will be one of the only slides I'll read from the deck, I promise, but it's a measure of the ability of a power system to meet electrical power, so the supply and the demand for customers. But the key word that we'll focus on today is within, well, I guess keywords, more than one word, is within acceptable limits. I will say from the get-go, there is never 100% adequate. There are no systems that are economical for us to never have shortages. And so the idea is, how can we measure the supply and demand and have it meet within acceptable limits? Now, key here is we need to make sure that we're modeling all the different uncertainties that we need to think about. And so this is the last sentence of this definition. It's taking into account scheduled and unscheduled outages of different components. And so really with this definition, we could have a simple illustration of supply and demand. Obviously, orders of magnitude are not important. In this case, it's from 0 to 5. Our load is the dark blue line, and our supply is the shaded light blue area. And what you can see from this example is on the contiguous hours, we have a few of those that we have insufficient supply to meet load. And at its core, resource adequacy or understanding adequacy is understanding and defining what are all these hours, whether it's one or contiguous, that we now need to understand. And I think for my own clarity, I'm going to not have my camera and see my head bop around. Apologies. Okay, perfect. And what you could see from here is that the green shortfalls, which again, I will use the word shortfall, deficit, and event interchangeably. And we'll talk about that in a second, but I will try to choose one, but shortfall, deficit, and event all mean these green boxes. Any hour or set of hours that there were insufficient supply to meet load. And what you can see here in our example is that we had 3 events that were 1 hour long and 1 megawatt. That's the 3 small green boxes. We had 1 event that was 2 hours, and I think, could you see my mouse? Just making sure. Crystal, or is my mouse visible? Okay, yes. Perfect. Thank you. You can see this event was 2 hours long, and the first hour was 2 megawatts. And then the biggest event was both 3 hours long. You could see we had insufficient in the 1 megawatt insufficient in the first 2 hours of this event, and then 3 megawatts in the third. Now, you don't need to remember any of these numbers as much as it's a quick visualization to understand when we're talking about adequacy. In any case, these are all simulated events. And so we might use the word model shortfalls, we could use simulated shortfalls, but in all of our resource adequacy work, we are never talking about real curtailments that will happen, but it's the risk that curtailments could happen. And so from the get-go, understanding the definition that when we talk about events, these are all simulated events. What they do tell us, however, it's the risk that the system could experience. And specifically, once we're able to define all of the different characteristics of the shortfalls, this can inform the types of resource acquisition decisions we need to make, whether it's additional resources for future portfolios, or a word that we often talk about, a concept we often talk about in the council, or it's to understand the emergency measures that are needed for you to mitigate potential shortfalls. And so resource adequacy for planners, and really the connection that resource adequacy, that as you'll see with the presentation, is to suggest what future resource decisions you need to make, as well as understand what is the emergency measures that not building resources could imply. And key here, as mentioned in the previous slide, is any RA analysis that really wants to dive deep into the challenges that systems face needs to incorporate the uncertainty of power systems. Are there any questions with this high-level illustration? No questions. When we're talking about power systems for long-term planners, really it's the bulk power system. Many of you will know this. This is really just to help connecting the dots to other parts of the section. But we're talking about supply and also supply uncertainty. So whether it's hydro and we have different stream flows, whether it's renewables that could have different wind patterns, even thermals could have their own maintenance schedules, but there is an uncertain component to our supply. On the load side, I see we shared icons with previous slides with load components. You can see that we have industrial, commercial, residential, figured cloud could be a good proxy for data centers, which we know are big in many parts of the region and of the world, the US and our region as well, and then EVs. On the load, it is also it's also important to remember that we have load modifiers. We do view them as supply resources, but they actually modify the load. And this includes energy efficiency, demand response, behind the meter batteries, and behind the meter solar. And so there are two big components that we're talking about, and making sure that we understand their uncertainties start with supply and then demand in this case, and how we modify that demand. Connecting them in the bulk power system, we have the transmission and distribution. Spoilers, we will not be talking about distribution. That is not part of bulk system RA planning. Very important topic, but not part of resource adequacy for long-term planning, as mentioned. But within transmission, we all know transmission is a big topic, and the question of whether or not certain capacity expansion projects will be there, or how and where to build supply resources based off of existing limitations, also play into the uncertainty of transmission. Climate is a big one, and the weather patterns and how uncertain and the variability we will see in the distribution that we need to model will play a big difference. This would impact stream flows. We can have more water, less water. We can have shifting of patterns of when the water would be available. We can have low wind, high wind, solar implications. And likewise, we can have higher loads given winter events, summer events. And so making sure that we understand the uncertainty of our weather data and how it influences supply and load. Market uncertainty, actually, I'm really glad we have components of NURC today, because there's a few things that we'll talk about that in the report that came out. Well, we won't be talking about the report, but there are elements that we'll talk about NURC in a little bit. But the realm of market uncertainty is very big, and understanding what exists outside your own region and how much you should rely on it. And then lastly, policy uncertainty, whether we have renewable portfolio standards, we have emission reduction standards, we have incentives for EVs and other elements. The policies that are out there will influence your uncertainty. And as long-term planners, really the question from this slide and the takeaway is, how do we represent all of these different uncertainties in one or two or multiple metrics? And really the idea is that understanding that risk of simulated shortfalls, given all of these different uncertainties, that's how we narrow down the world of adequacy. Scope matters. As mentioned, you can see from all the different icons, lots of things are in scope, whether it's utility and community side resources, behind the meter resources, load, transmission, market, and as we will discuss as well, temperature sensitive correlations. What is out of scope typically is really the distribution network. As I mentioned, very important. We often asked about, wait, what about a downed tree or a frozen line? They can have life-threatening impacts, but they are part of operational decisions, and different metrics capture distribution. It is out of the scope of resource adequacy for long-term planning. And as mentioned, sub-hourly operations. Really, we won't be talking about frequency and stability. Long-term planning tends to focus on 3 to 5 and 10 and 20 years. We have short-term, medium-term, and long-term planners. They might have different thoughts and perspectives. And here, as the name of the presentation, this is for long-term planning. And so we get from no shorter than the hour level. If you were wondering, what about extreme events? Because it is a question that also comes often, whether it's a cold snap, polar vortex, heat wave, and wildfire, there are things that could be considered in scope to an RA analysis and out of scope. What would be in scope is if we have the ability to quantify the impact on load and wind, as well as gas pricing. We all know that there could be gas limitations in specific challenging conditions for a variety of reasons, but what could be in scope in these cases is making sure you understand how those phenomena impact load, wind, gas pricing. And wildfire is an interesting one, because it's one of those questions where, is it resiliency? Is it part of adequacy? And the question here for all of these phenomena, there could be other phenomena, there could be earthquakes and other things, right? This is why we're focusing on weather. Is the question is, at what point is your distribution incorporating or not incorporating these extremes? And one way to look at it is if the data you use includes these extreme, these very high multi-day temperatures or multi-day cold temperatures, you might not need to do a standalone stress test. And if it does not, you might ask yourself, should I do a standalone stress test? And then that becomes a little more like a resilience study. Wildfires, we do suggest really need an important question of whether or not it's a resiliency study. Like, should we assume it's going to happen every year? Or, is it one of those things that the frequency isn't as big? The purpose of this slide isn't to say you have to include these in your studies as much as it's an encouragement that when you're thinking about resource adequacy, you want to think about the extreme events and you want to ask yourself, are they incorporated? If not, how should they be incorporated? Putting the high level behind us, but we'll get back to some of these levels. At its core, adequacy is important. We saw this in the first few slides. The risk from adequacy informs our resource decisions and it informs our operations. If you're thinking about the types of costs that we can have, and where this is a very large simplification, the light blue line, we will consider those the capital and operating costs. We have cost on the y-axis, we have added capacity on the x-axis, and the idea is a system that has more and more capacity will also have increasing capital and operating costs. Hence, we see this increasing curve, this light blue curve. There is also an implied notion that every time you have a shortfall or when you cannot satisfy load, that has an implied cost. The more hours that you can't serve are costlier to consider. And so this is what you consider, this is what you can see as the load curtailment cost. The more megawatts you have, and in other words, the more resources you have to satisfy your demand, we could assume that we're going to have less shortfalls, and hence the load curtailment cost will decrease over time. There is a point, as you can see from the top line, that suggests an inflection, some balance where there's enough megawatts that the cost seems to minimize from a total cost perspective. And from an adequacy side, we can see that a lower investment in resources, so the left side, of the graph might lead to lower adequacy because we still have high curtailment costs, and a higher investment in resources could suggest lower curtailment costs as well as higher adequacy. The question, though, is, or the challenge really is, curtailment cost is a really elusive concept. We'll talk about it in some of the economic considerations for adequacy metrics, but it is substantially easier to measure curtailment dimensions. And so this is why, even though adequacy and making sure we have an adequate portfolio is directly related to overall costs at the end, adequacy metrics tend to not focus on costs. I do see a question over in the chat. 1 second. Okay, so there's a good question about gas price as a risk in the scope. It's the only cost that is in scope. Please help us understand why this price is in a scope. It's a great question. We will get back to it in the types of tools and philosophy that we have. But depending on the model that you use, and if you could introduce different costs for resources at different times, you might model higher gas price in winter, for example. Or you could say that there are instances where we assume that the pipeline may not be as available. You could either physically remove megawatts from the system, again, the simulation, not real life, or you could signal higher prices. So that's the in scope. Nicholas, I see your hand.
Yeah, along the same lines, one thing that happened during the Martin Luther King Day event is that we experienced some marginal cost prices from imports. And I'm just curious, do you think about sort of when the system goes, quote unquote, from sort of marginal cost pricing to scarcity pricing and how that might affect, decision making?
It's a good question. I think it could affect decision making, as we'll talk about from an adequacy perspective. There are adequacy metrics that could consider costs, and so I know it's not a direct relation to your question, but yes, scarcity pricing will influence risk and how and what resource decisions we might make. Another question, proxy, yes, price would be a proxy in this case for whether it's transportation scarcity or availability scarcity. So price is one of those really interesting ways that we think about capturing risk in adequacy models. And this is true for resource costs, not just gas. So price is one of those really interesting levers we can test. Don't see more questions. Okay. Recognizing that costs.
Quickly.
Yes.
Quickly, is that because of mainly a lack of data availability or accurate models on the gas side to be considering something more like the physical system conditions?
Great question. You're leading to the latter part of the presentation, and it's about the tools that we have. So yes, there are different granular levels of granularity and complexities. Gas networks is one of those. I don't have to use. It's not unfortunately, but gas networks is a little trickier with some power models for simplification. So yes. Okay. Recognizing that there is this philosophical challenge, it raises another question that we could be a little more nuanced, and that is, can a system be overly adequate? And if we assume that some large new load is introduced to your territory, you're going to be faced with a decision on adding capacity. So we start at 0, and we can go all the way to this ambiguous more on the left. And whatever adequacy metric you are using, I have yet to see an adequacy metric that is below 0, but we can be creative and try to find one. But let's assume 0 is the smallest value your metric could be. And as you go farther away from it, you are less and less inadequate. But whatever your metric is, you're going to have a criteria. We can start with loss of load expectation of 0.1. We will talk about it in a few slides, but assume that that is your metric. Remember that you have some total system cost, again, a little opaque, but it is there. And if you first decide to put resources that do not satisfy the metric, you will not only be inadequate, but you will likely also be more expensive. You could decide to invest in a lot of resources and see that you're actually past your criteria, meaning you're over and above satisfying your metric. Let's say our criteria in the middle is 0.1, we're at 0.03, right? It's great, we're adequate, but notice that your system cost might likewise be higher than it needed. And so the goal with adequacy criteria and really the idea from various perspectives is to try to have a portfolio that just meets the standard. Now you can talk about if 0.11 or 0.09 are very different from 0.1, philosophically speaking, but the idea to take away from this slide is you're really trying to be at a point where once you set a criteria, there's no financial need to be beyond it. However, meeting the criteria does not necessitate being at the minimum cost. This is just a visualization. And the question that we have as planners, this is true for many planners, right? Not just resource adequacy, but the reason that we need to be so detailed and nuanced is how do we right size the system so we don't overbuild or underbuild? Because whether we underbuild or overbuild will have direct implications to shortfalls and simulated shortfalls, but also to ratepayers. And the idea that it's possible to overshoot and undershoot really should be in our minds as adequacy planners. Now we get to dig into the metrics, and after this section, I think we'll have a break, but we can go with the flow. I already used some of these words, but an adequacy criteria is made up of 2 components. It's the metrics and the thresholds. We could view the metric as a measurement or a statistics of the distribution of simulation shortfall quantities. I know it's a mouthful. We don't always need to say it. Think of a metric as a measurement from a statistical observation, and we tend to talk about frequency, duration, and magnitude of simulated events. Thresholds are just that target that we use as a binary above or below. Sorry, you could be at, but it's just that number that you're using as the target that would satisfy adequacy. The role of adequacy criteria, and I like this little doctor stethoscope, I think that's the word, is we use that to assess system risk. You know, we can talk about it as health or other perspectives, but really the idea is we have metrics and we test different parts of the system, or we test different characteristics of the shortfalls, to be a little more specific, and they tell us, are we adequate or are we not? There are 4 main categories of adequacy metrics. We're going to go through some of the more common ones. This does not mean that there aren't others that are out there, but really these are the bulk that are good to start with. We have the annualized metrics, which we could summarize as these are expectations, and most of you would be familiar with many of these. We have tail end. Remember, we said adequacy metrics are distributional, and so an average is just a measure, is still one observation from a distribution. We have tail end metrics that look at the extreme or the largest values of observations. We have event-based, which are interesting and need to be a little more sensitive with how we use them. And then we have economic metrics, which I have a soft spot for, but we'll talk about the challenges of using economics from an adequacy metric perspective. Each one of these slides is going to have that little icon just to help follow along of what part of the metrics, what family of metrics it falls under. Most of the metrics that are common today in the industry are annualized metrics, and they fall under three aspects of curtailment statistics. Curtailment observations. Frequency is the most common one. Loss of load probability, or LOLP. The way we tend to interpret it, though in the next slide we'll see the actual mathematical definition, but the way we tend to interpret it is expected number of hours, days, or years. The council has previously used years, with at least one event per simulation year. And so it basically is a measure of how often we would expect that, from a year perspective, that a year would have at least one event. The more common frequency metric in North America and in many parts of the world is the loss of load expectation. This is LOLE. Likewise, I mentioned all of these are averages. Apologies for the repeated language, but it's the expected number of event days. And this is an important distinction. It's a day with at least one event per simulation year. And rounding up the frequency metric here is the loss of load events. This is what the council uses, and we'll discuss why in a few slides, but it's the expected number of events. So it's not event days, it's expected number of events per simulation year. None of these metrics tell us anything about duration and magnitude. They have their strength, but these are all expected-based frequency metrics. We also have magnitude metrics, and it's really the same metric, just with 2 different ways of showing it. We have the expected unserved energy, EUE, and it is the expected number of event magnitudes. And so we look at all the unserved energy in megawatt hours, and it's the expected number of unserved energy in a given year. It is not apples to apples, or it's not a fair comparison to compare one utility's EUE to another. And so that's why there's another way of using it, and it's normalizing it. It's the NEUE, and then it's a little more apples to apples. It becomes a percent of load that is easy to compare. And notice again, magnitude tells you nothing about frequency or duration, which leads us to the 3rd annualized metric, loss of load hours. It is the expected number of event hours per simulation year. And all of these metrics, I believe if you look at many IRPs, both in North America and others, utilities report them. not many use all of them or use them as their criteria. And as we'll see, it's really the loss of load expectation that tends to be used as a criteria, meaning you determine adequacy by whether or not you satisfy it. The other magnitude and duration metrics tend to be reported only. Now, any high-level questions here, or we're just going to go a little bit more into each one of them?
Not a
Okay.
question, Dor, but if you're
Oh.
monitoring the chat, I just wanted to let you know that I dropped a snapshot of the annual metrics and thresholds that NERC uses for its seasonal and its long-term reliability assessments. They're very closely related into the chat, just for a specific example of what you're talking about right now.
Perfect. Yep. Thank you. Great. Great addition. I will say there are suggested readings at the end of the slides. The NERC report from or the NERC description of the probabilities and adequacy metrics is highlighted, and I will give a shout out to NERC as well. I'm under the impression that you are revamping, or there's going to be an updated to that document, but we could talk about that at the end. But yes, there are suggested readings at the end of the presentation. A little bit more mathy, and I promise the more accurate definition of loss of load probability is the probability of 1 year having at least one event. I know before it was the expected, but technically speaking, it is the probability of any 1 year having at least one event. We sum all the simulations that have at least one event, and we divide by the number of simulations, and that gives us a percentage. I will say, and you can actually see it from, if you haven't seen the picture in the channel, there are two ways to measure metrics: deterministic and probabilistic. That is the second part. That's the second part of this section. But here I'm showing you just kind of the simplified mathematical way to calculate it. It is reported as a percent. So, for example, the council's previous standard was 5% LOLP. Really what this means is the system was adequate if the probability of having at least one shortfall in a given year was at or below 5%. On average, that gets translated into no more than 1 year out of 20 with an event. And so you can start seeing how different language, and we'll see it more with the tail end metrics, but how a definition can have an interpretation that sounds a little different, but on average, it's easier to interpret than just probabilities. I mentioned this in the overall slide, but none of the frequency metrics actually have insight into magnitude, duration, and what's more importantly, with the loss of load probability specifically, it doesn't give you anything about within year expectations. There's no way of knowing if the year had one event, 1,000 events, or 2 events. It's just whether or not the year will experience challenges. And this is the bottom line is true for all the other frequency metrics, but you could have many portfolios with the same frequency value, whether it's 5% LLP, 0.1, or whatever you use, but they could have very different duration and magnitude metrics. The conventional understanding of loss of load expectation and loss of load events, there is a theme here. You can see it's really summing whatever you want and then dividing it by the number of simulations, and that will give you the expected metric. And generally speaking, loss of load expectation is the most common. 0.1 is the most common threshold. The way to interpret it as the expected 1 day in 10 years, that's a loss of load expectation, or expected 1 event in 10 years. 0.2, for example, gets translated to an expected 1 in 5 years. These are independently set from economic considerations. And we'll get back to this in the economic metric, but I do want to stress it again. And I did mention some repetition ahead of time, so you have to excuse me because I already apologized for it. And what's important to know is that this is really a shout out. It's this comment is just good to keep in mind because it might come up every now and then. There were some past ambiguities about connecting LOLH and LOLE, specifically comparing the 2.4 LOLH to 0.1 LOLE. They are not comparable. in hindsight, I didn't put the paper in the suggested readings, but I can after the break I can find the paper that colleagues and I believe a few other colleagues, people in the industry wrote clarifying this interpretation. And so if you still find this comparison of 2.4 LOLH to 0.1 LOLE, it is not apples to apples. Specifically visualizing these because they're worth a second look, because many utilities use LOLE. The wrap also uses LOLE, and so little visualization on how are they actually different. Let's take a 24-hour day. Shortfall is the salmon color. On the left, this is how we count events towards loss of load events. On the right is how we count events towards loss of load expectation. In this case, both of them would see only one. Likewise, in this case, where the whole day had one long deficit, both of them would see it as one event and one event. Things get trickier when there are multiple inter-day events. Now, the maximum amount of events you can have, theoretically speaking, in a day is 12. Otherwise, you have to have non-sequential hours to have multiple events. And so you could see that loss of load events would measure this as 12 different events, whereas loss of load expectation would still see this as one event. We shouldn't say 0.1 for loss of load events because loss of load expectation gets another point for being a little more nuanced in this case, where you have 2 days, but the event crosses over. Loss of load events would see this specific 8-hour event as still one event, whereas loss of load expectation would see it as 2 days. And so this isn't to say that loss of load event is always better than loss of load expectation. We, as the council, do use loss of load events because it works well in combination with our other metrics. And so we do think this slide is helpful to visualize the difference. In many simulations, the LOLE and the LOLEV are exactly the same. In the case where there's only one event in a day and that there are no events that cross over, but there could be some variation. They tend not to be, night and day. But I do want to call out that there are differences between them. In terms of expected unserved energy, it provides insight into the average unserved. And so we sum all of the energy that couldn't be supplied, we divide it by the number of simulations, and that gives us the EUE. As I mentioned in the overview, it's not fair to compare a small utility's EUE with the large utility's EUE because 2,000 megawatt hours could be substantial for one, and it could be very insignificant for another. Again, 2,000 is arbitrary. You can choose any number. To normalize it, you divide the metric by the average load and you multiply it by 1 million. And this does get reported as parts per million. And it is less wildly used as a criteria, meaning within your criteria for adequacy. It is less widely used in North America and Europe. You can find instances that use it. There are countries outside of these regions. I believe two of these numbers are Australia and India, though I'll double check. I flagged there's a really nice EPRI report that summarizes different countries and different regions around the world and their metrics. And so you can see that you can now start comparing more apples to apples. Oh, it's 0.002% or 0.05%. And so for those who do use EUE, they tend to normalize it, and it is, I lost my train of thought. Oh, sorry, 1 second. It is still reported. I mentioned before in the overview, many of these metrics you will find reported in IRPs or adequacy work. They're just not the binding, or they're not the metric that's used to say we are adequate or not. It's just this happens to be what we're also seeing. Loss of load hours. Again, insight into the average duration of an event. Elisa, did I go back?
Yeah, go back one, because I do want to kind of like, isn't a megawatt, even I understand that a megawatt for one utility or 1,000 megawatts, if you're small, that's a bigger deal. but 1,000 megawatts is still 1,000 megawatts, and what makes it up is the number, of customers. So if you think about it from a customer, like, a person who's having an outage, why does it matter whether, whether it's, okay, one utility that has 100 customers that make up that 1,000, let's say, or whatever, and 100 for a bigger utility? I mean, it's still like 100 people.
That's a good question, and the idea behind normalizing it is to try to have a relative playing field. When you can say so think of it as, if you don't know the percent of the average load it's satisfying, it's harder to conceptualize it as how big is the challenge. If it's it's a tiny fraction of your load, you might think of it as it's not as difficult to find a solution for. Whereas if you just say, it's X megawatt hours, like, okay, but how much more resources do I need out of my portfolio to satisfy it? And so it's a great question. You're right that the customer doesn't care that their shortfall gets divided by the average load, because they would experience a shortfall. But it is a way to help compare perspectives. And a utility that uses a magnitude metric such as EUE or NEUE would still, be adequate to solve it. But it really is used, the normalization is more of a literature tool to compare across utilities. It is less on what the customer specifically is experiencing.
I see. I think I understand. It's really around the ability to solve the problem. High NUE is harder to solve for the utility, much more expensive than a small NEUE, I think is what I'm hearing.
Yes, yeah, we could derive it that way. So the idea is, if it's not just the megawatt hours which need to be addressed, but it's how, is it a drop in the bucket, or is it a wave coming at you? That's the way to see it.
Thank you.
A great question. Okay. Loss of load hours, as mentioned, it's the average shortfall duration. This is more widely used in Europe. And again, it's the same EPRI report, which I recommend reviewing. Values tend to range from 3 to 8 hours, but if I'm not mistaken, we've been on several working group calls and other adequacy issues. Even though the metric is that high, it rarely gets used. It's never binding, because the systems end up being a lot lower than this. And so maybe I'm doing a disservice to how I explain that, but if you look at the report, you will see about 3 to 8 hours. But broadly speaking, those systems are operated in ways that the LOLH metric is substantially lower. It is a criteria, but it tends to be much lower. And this is where we can start talking from a duration perspective, where it could have a connection to economic metrics, as specifically the value of lost load. I do want to say, if you do speak with your European colleagues, loss of load hours in some instances is considered a frequency perspective, and there are slightly different ways to conceptualize. And so there's a chance that you're talking about LOLE for North America. It's the interpretation for LOLH in other parts. So just put that in the back of your minds. But for our perspective, LOLH is a duration metric, not a frequency metric. Any questions on expected metrics before we jump to tail end? Okay. Tail end metrics, they capture the large events. There are two main ones, and we've had really good discussions over the years in our advisory committees, but the first one is value at risk. And what you're seeing on the right, these are 5 different portfolios. They are arbitrary. You can see that they have different largest events. So this is called a capacity duration curve. I know the word duration is confusing, or it's misleading. This is not hours, but it's that when you stack all the maximum shortfall capacities, this is the curve that you get. And you can see that while they all differ, with the top dashed purple having the highest largest deficits, and then it goes down as we vertically go down the line. All of them, however, share the same value at the 97.5th percentile. Now, you will see 97.5th, but you're seeing that the x-axis is 2.5. All of these metrics could be swapped. So if I say 90th from the highest, that could be the 10th. It just depends how you're talking about it, but it's the mirror of 2.5 is 97.5. And so all of these share the same observed value at the nth percentile. In this case, it's 500 megawatts. Conditional value at risk is now averaging the value of observations above the nth percentile. That was difficult for me to say. I don't know why. And what you can see here on the screen is that the average of these five, the lowest is 534, and the highest, again, the purple line is just shy of 870 megawatts. Depending on which one you use, you can now start to differentiate. The way that we view the tail-end metrics is it's just a statistical tool that you can apply to your duration, to your magnitude. In fact, most often it is used from financial perspectives and portfolio optimization. So you can use the CVAR to minimize financial risk. So really, VAR and CVAR, they're agnostic to what metric you're using. You could choose how to apply it. But the way to view it is the VAR value. The interpretation is X years out of Y durations or magnitude, you'll be less than Z. I know it's not a fun sentence to say out loud, but we can look at the example on the right. 39 out of 40 years, the largest peak hour shortfall across these portfolios would be 500 megawatts. In other words, only 1 in 40 years would we expect to have a shortfall that is higher than 500 megawatts. That's how we interpret the VAR value. It is a clear line in the sand that says, are you above it or below it? CVAR is a little trickier. It's not quite, you could say it's a sand in the, there's a line in the sand, but once you say what average extreme you want to avoid, it's viewed the same way. So it's the Z average of the highest end percentiles. Notice, however, that when we started this presentation, we said you can never satisfy all events, right? A system will always have an event that is too costly. If you use the VAR, it means you are not trying to protect against values above that. You're not trying to protect against shortfalls above that limit. If you use the CVAR, it means that your limit will include events you may not need to mitigate. And we can spend a little time on this. This isn't to say that VAR is always better than CVAR. There are instances where CVAR is perfectly adequate to capture what you want. It's just a nuance to reflect that VAR value does not, it means that you're not trying to protect against, again, I'll use my mouse, the fact that there's a 3,000 megawatt deficit here, if you happen to satisfy it, it means that it's so infrequent, you are not trying to protect against it. Whereas if you're using the CVAR, you could say, I know I'm not trying to protect against it, but it's going to push my entire financial, it's going to push my entire shortfall threshold up. Am I okay with it? That's just the nuance. And I think this is a great topic to discuss in the second section when we start seeing what are we really trying to protect against. There's no standard, but as you could see, the 90th, the 95th, 97.5th, and 99th are more common ones. And again, remember that it's also the 90th can be reported as the 10th, the 95th as 5, 97.5 as 2.5, and 99 as 1%. It's just from which side of the distribution you're looking at it. Any questions? Okay, we're close to the break. Event-based metrics, I'll go a little faster here. We basically define a duration and magnitude that is unacceptable. The idea is to, for example, avoid events that are equal or greater to some duration, some maximum peak, and some energy unserved. It is used, but it's tricky because frequency of these events is a little bit more elusive. You need to ask yourself, is there any frequency of these events that is allowed? And more specifically, for the events that are events, but they don't meet the criteria, meaning they're less than all of what you want, do you still count them? And if those happen too often, are you still adequate? So this is by no means to cast a negative light on event-based metrics. They could be very powerful. It just means that you need to consider frequency a little more carefully than other metrics, because this does leave room for whether accidentally or by decision, not counting all events, only counting the bad events. Economic risk is the last one, and I did say I have a soft spot for it, but maybe in a few years we'll have more, just more insight on how to use them. I brought up a relationship to LOLH, value of loss load, that's VOLL, could be used to set a duration limit. Value of loss load is your dollar per megawatt hour that you would pay someone because of a shortfall. You could already start thinking of what you pay a hospital would likely be different from what you pay potentially a data center or other industrial uses or custom, homeowners or renters. So there is such a big variety of what that value of loss load could be that it's tricky to use. But the idea here is that if you know how much new resources cost and you know how much your cost of a deficit is, you could try to optimize the length of a duration that's acceptable. But it's very difficult to assess, and you'll see a few not warning signs, but a few more texts will pop up as we discuss economics in general. Another way to consider economics is from a tail end perspective. And this doesn't have to be what we just spoke about with the VAR or the CVAR, but they could be used for it. And this is where we start talking about scarcity pricing. You could decide that you are inadequate if there is a certain electricity price that happens too often in your system. And so, for example, let's say we don't want to go above 1,000 megawatt hours. So, if your model is able to dispatch resources and you have high confidence that those costs are nuanced enough, you could see what hours, if they reach that value, and if they are too frequent, you could say it is inadequate because we are having high costs too often. The challenge, and this is true for scarcity pricing as it is true for value of loss load, it is very difficult to determine, and it is subject to modeling limitations and sensitivities. I think there's really good work out there, and you could look at different surveys and willingness to pay and other considerations, but at the end, it is very difficult to tie specific economics and financial considerations to adequacy metrics. And what most planners do is deciding on metrics and thresholds from a disconnected or from an indirect application to cost. So I mentioned before, LOLE, LOLEV, LOLP, they have no direct cost dimension to them. It's not the end of the world, because what planners do, that was funny to say those two words together, but what planners end up doing is they don't ignore economic risk. It just doesn't get captured from an adequacy perspective. Instead, it is handled in the capacity expansion, the portfolio optimization models, where they need to satisfy many constraints, including the costs. And so that's how, if the takeaway should definitely not be adequacy doesn't care about cost. It does. But models that optimize power systems include those. And so it is captured, just not directly from an adequacy metric. We'll see what happens in the future. But currently, this is kind of the industry approach around these. The last slide before a break is that no single criteria tells the full story. I think this kind of came up naturally by itself, but frequency just tells you frequency. Likewise for duration. And how many times would we need to rely on emergency measures is a very important concept. We'll talk about those right after the break. But that wouldn't tell us for how long do we need to use them. And likewise, it doesn't tell us how deep we need to rely on them. And because of this, the takeaway is that using multiple metrics does help to understand the full story. No, you do not need to use all of the metrics we just discussed today, but using them and choosing appropriately really helps to paint the full story. And I think on this note, we're good from a break unless there's any questions. Appreciate all the quick back and forth over there. I might speak a little faster now as we go through the topics, so we make sure we get through everything. Apologies on that side. takeaway from this slide is adequacy takes time. We're not going to go through all of these, but know that even the council, about 20 years, almost 30 years of using unofficially expected load resource balances. We'll talk about those. That's a deterministic way. It's really around early 2000, late 90s that we started doing probabilistic methods. And so that too was over 10 years of using loss of load probability. And only as we were responding to changes in the region did we start using multiple metrics. And so again, it's just an example that utilities can go through these different evolutionary cycles. There's nothing wrong with it. You don't need to feel urged, but just see it as industry is moving and utilities can take time as they evolve with their adequacy approach. The reason we need to evolve, the reason evolution happens is when our risks change. For the longest time, from council perspective, region perspective, the main risk was just coincident high loads with low water. A system that is heavily hydrothermal and EE, the uncertainty is a lot different than when you have a system with lots of renewables, changing political policies. And as the risk changes, so too the need to understand how to requantify the new risk. So basically moving from frequency to also looking at magnitude and durations. The key here is that these could be tailored to your utility. A shortfall risk in size for one utility does not have to be the same for another. We talked about that from the normalization of the EUE, and a metric and threshold for one organization may not be most applicable to your organization. It could, but it doesn't have to be. And really the key here is that the modeling capabilities and the data sources and assumptions you use will influence, or I can be a little more open-minded, can influence your decision about what metrics you end up deciding. There are two calculation methods, deterministic and probabilistic. Probabilistic is really where the industry is going. View the differences as deterministic, as simple accounting. Simple doesn't mean bad. It could still be very good depending on your system. But that's where you have the expected load resource balance. When you have less uncertainties and you don't need to worry about fuel accounting or the chronological nature of a system, deterministic approaches, they capture that well. Whereas probabilistic incorporate future unknowns and uncertainty. I mentioned this industry is moving towards probabilistic methods, and while there's no standard, we said the LOLE, which is a probabilistic method, is the main one. Within the methods to assess resource adequacy, the deterministic really compares expected availability to expected demand. And the connection here, and this is a shout out to Elizabeth in the beginning, planning reserve margins and what happens after the assessment. This is where we also have a deterministic approach to our reserve margins. They tend to be based on peak hour demand, and there's a building block approach. This 15 to 18%, give or take, and it's the needed surplus. It's the percent above load that you need to protect against the surplus of generator outages, extreme temperatures, and then the balancing and contingency reserves. This is deterministically calculated. Probabilistically, we can use analytical tools, which are the shortfall probability function. This is one of the questions we had in the list. And we could also use simulations. The most common is the Monte Carlo chronological hourly simulation. And here, the planning reserve margins, which again is that percent above load, that's the direct connection between adequacy results and our portfolio expansion models, the planning reserve margins are now derived probabilistically, or from probabilistic metrics would be a little more nuanced to say this. The analytical methods could also be called convolution, and the idea is you create your resource availability duration curves and your generation duration curves. You morph them together, and you basically derive your adequacy metrics mathematically from distributions. I mentioned the NERC report at the end really maps the mathematical way to do so. We're not going to spend time on it today, but you can calculate most of the or many of the metrics we just discussed convolutionally. That's not a word, but you know what I meant. One place to do these over Monte Carlo is if you don't care, again, about if the link between chronological, spatial, temporal, fuel accounting isn't as important because of the type of system you have. Convolution is more straightforward. You don't need to model it from a simulation perspective. Now, the opposite side is when your system, you do want to capture the chronological nature of the system. This is where Monte Carlo hourly simulations come into really their pride and glory. You can run multiple iterations, whether of one operating year or different operating years, and you cycle through different uncertainties, different loads, stream flows, for example, wind and solar, forced outages. There could be several variables that are important for you that you cycle through them. And to the question about where we get our distributions, this, when you run it thousands or hundreds or dozens of times, this is how you create the shortfall record to get the distributions from. And now the shout out here is for the really interesting, we had the IRP, PNUCC IRP workshop a few months ago, which I'm blanking on the full name, but a topic that came up there when we were at PDX was asking of, what is the role of complexity and can we be too complex or under complex? And many of these models can take days to run. Some of them can take hours depending on the setup, but the takeaway here is we don't always have to model every single possible iteration or combinatory relationship of input variables. And here we can think about testing correlated data. And this would also provide a more nuanced result, and it could also reduce the sample size from thousands to hundreds potentially. And so this is just a reminder when you're discussing the modeling tools that you have, thinking about the input variables and how you capture correlated uncertainties might minimize simulation time as well. How we choose our criteria, on the one side, it's the tools, and really there's no way around it. Different tools have different strengths. And if you're using your own in-house, which could be perfect, there's nothing wrong with in-house tools. You could be using a commercial tool or a consulting tool. I'm sorry, meaning a consultant. That is the tool here that uses their own tools. These are something I believe we'll discuss in a future session, but know that the tools that you have would influence what metric you use. Because if you can't calculate distributions from your tool, that would lead you potentially to a deterministic approach. And if you can then choose appropriately or from that list of options. Philosophically speaking, this is what we'll spend the next part of the slides, and it's the philosophical approach to your shortfall risk. And this is really where your utility can, you as a planner can come and shine with the utility and say, and just ask the questions, what are we trying to protect against? I mentioned the emergency measures, and we'll talk about them. I know I keep saying it, but if not the next slide, then the one after, I believe. But the idea is understanding what can you do at time of emergency. And the question here is, we'll see, is it a resource that's already included in your active portfolio or not? But understanding when push comes to shove, how much you can push back is crucial. The second question is, how often do you plan to push back on it? Meaning it's the risk tolerance we have for how often we want to rely on these really expensive things we don't want to do, but we can. And this leads us, as promised, to the emergency measures. There are a list of actions that utilities and decision makers can do. And these come in from this image on the right. Reminiscent of the image in the beginning, here we see the load on the right. We have different resources on the left. There's a gap. And so hypothetically, this is where your emergency measure would take into effect, so you mitigate the shortfall. The key is these are not modeled. Many RA models have reserves, so balancing and contingency reserves are included, in this case, thermal and hydro, but emergency measures are not modeled. And what are these emergency measures? A low lift, or what's typically in a utilities control, is higher operating cost resources you don't want to use on a normal day. It could be high-priced market purchases over a limit that you have, buyback provisions, backup generators. These are all emergency measures that you typically do not model as an active resource. You keep it, you know it's there, and you will use it if needed. These are separate from the heavy lift, the less desirable. When we call for conservation, we reduce load. These are emergency measures. And the idea is to connect RA metrics and the risk that we get from the statistics to understanding what emergency measures are available to you and how often. And so the frequency metric will tell you how often you would need to rely on one of these options. duration, how long would you need to rely on it? And magnitude is how much. Important, and I apologize for running, but I will run a little, is that demand response program are wonderful, but if they are in your active portfolio, they are not considered emergency measure. So if you have a DR program and your model already accounts it, assume that your simulated shortfall still happened. And so this is why I'm saying if DR is in your portfolio, it is not an emergency measure. What we want to ask as planners, whether you have your metric or you're about to embark on your journey to find your metrics, it's how often will you accept shortfalls? Reminder, never is not feasible or an economic option. And so there will be a frequency metric or a frequency number that will likely satisfy your risk. And you could also ask, what is the extreme or the maximum shortfall characteristic I want to avoid? Is there such a thing as too long, too big, too much unserved energy? And each utility might have its own answer to all of these. This goes back to, we don't need to take, what the council is doing. We've done, as you saw, multiple years of work. We're not suggesting everybody adopt that blindly. You could ask the same questions and use the processes to determine what is your risk tolerance. And the connection here is we have the metric, we have the threshold, and tying them is how often. The threshold question, depending on the metric, is how often you want to avoid them. For those of you who are not familiar with this wonderful board game, I suggest you do, one of my favorite, Settlers of Catan. And as you know from the board, your position matters. And from a market perspective, deciding how much you rely on your neighbors to give you wheat or sheep, in this case, megawatts when you need them, is tricky sometimes. And so whether you're short or long with capacity or energy will influence how you view your role in the market. And if your portfolio is more based on firm contracts, that's a different market risk if you're on spot trades. And so you can see here, for example, Catan can also have spot trades. And if you need to rely on a challenge, how often do you need to rely on it? And the question here, now we put the joke aside, is do you want to have as a utility some market reliance limit? Meaning, the market is out there, but do you want to rely on it in your time of need? And if yes, is there a limit? As an example, the council uses 2,500 megawatts in winter and 1,250, so 1,250 of import limitations on the summer, because we say we're not fully aware of what happens outside our region at any given hour. We don't want to always rely on it because it might not be there, so we're setting a limit. So these are questions that you too will ask because this will influence your adequacy perspective. This is where we often get asked about ELCCs and how are they incorporated in long-term planning? The short version is that ELCCs is the effective load carrying capacity. They are not an adequacy metric. They are a measure of accreditation. It captures the percentage your resource is expected to contribute at times of need, and they are handy. You could use them to derive ELCCs from adequacy studies, and then you feed it into other models. You could use them to deterministically analyze your expected load resource balance. However, they are sensitive to your portfolio and the types of resources. The amount of resources added changes, so there's diminishing returns, and they're a little difficult to generalize. For long-term planning, it's still okay to use, but you're not going to use the ELCC from an adequacy study to make your final decision on what resource to actually buy. It is giving you the high perspective on how to credit your resources from the portfolio optimization. Is there a question or did I miss something? Okay. We'll get back to ELCCs. Again, they're used, many of you, you report them in your IRPs, but they are not an adequacy metric. They could be derived from adequacy studies, but they are not a metric. Broadly speaking, your path to developing RA or a suggested path starts with an initial consideration. Understand what's out there. And understand what modeling tools are available to you, which feeds into the vision. Ask the questions of what it is that you want to philosophically protect against, and then develop your preliminary criteria. Long engagement strategy, internal, external partners, exploratory analysis. There's a reason the arrow goes both ways. And as you saw from the council's example, 2-3 years and even more finally led to a final RA criteria. The way that we went about it is through surveys. Many of you and your organizations received surveys from us a few years ago asking for feedback. And so we had individual meetings, surveys. We met with organizations like PNUCC and others, aside from utilities, the PUC. So you really want to make sure you cover your bases. And it could be, as a council, we don't have customers per se, but you want to make sure from your own IRP processes that you're engaging with everybody to understand their own risk and how it relates to yours. The purpose of the survey that we went through was really to get feedback on our provisional vision and adequacy criteria. And the goal was to quantify the emergency measures and understand our thresholds. Questions include type of specific problems, what are you most concerned about, again, market, transmission, all of these different things that you could find your own questions, but the goal is to define the risk you're trying to protect against. This is where it comes back to the metrics. Some of you have seen this before, but trying to say key and goal in the same time. The goal is to map the available metrics to your risk protection goals. If you want to protect against big capacity shortfalls, event-based metrics and average metrics might not tell you that. If you want to do big energy shortfalls, event and tail end will tell you that. So we don't need to go through all these, but you can see that once you know what you want to protect against, you could then select which adequacy metric satisfies it. We mentioned this before, no adequacy metric tells you everything. You could choose multiple metrics. And in fact, what the council ended up choosing was the loss of load events, the VAR values for energy duration and magnitude. And so again, I know I'm running, but this is the idea. You have the metrics, you have your goals, and you could start mapping them together. We won't spend time on this. This is the metrics we end up using in the thresholds, but the idea is that once you're solid with what you want to protect against, it's that much easier to map the metrics when you also know the tools you have. This is the last slide on this section. I know it's 10:30. I could skim the rest, but Eliza, I will defer to your judgment.
Can you hear me? I realize that my mic's been on, so I hope I haven't been disturbing everybody.
No.
I mean, yeah, I guess I kind of leave it to the group. Do you have any questions? Do you want to revisit anything here? I would say let's go ahead. If you think you can cover it, in 20 minutes, I think you probably can.
Okay, I will do it. Okay. Now, so we covered the types of metrics. We covered the philosophical journey. We went and others go as well. Again, this is not to say that we're unique. There are many organizations around the US who are going through multiple metric analyses or processes. Now we get to conducting the assessment itself. There's two roles that we see to assessments. There's the adequacy assessment, which I recognize is a little geared to our council's language, but it holds true. You ask yourself, is the system adequate, right? You're looking at a future year, you have your strategy. Are you adequate with it or not? A needs assessment, this is where you say, I don't know what will happen in the future. Let me understand it. I look at what is existing today. And there's going to be a gap. And so the needs assessment is to tell you what adequacy needs you have for a future year without doing anything today. So this is actually what the council we were working on with our needs assessment. The overall flow, again, this is the power plan, but this is structurally similar to any IRP. There's a process that you do in your needs assessment, and your adequacy assessment come in the middle and the end. The middle in the case is that you use the needs assessment, as mentioned before, you use the adequacy results to directly relate it to the planning reserve margins or adequacy reserve margins that feed into your resource decisions. And then you also want to test the strategy when you finish. Now, we'll talk about how we test it, but this is the overall flow of resource adequacy. It's a key point in the middle, technically speaking, of a flow, but it's the process you need to do before your resource decisions, and then you test it again. You really need to capture the existing system. We're not going to go through all of these. These are icons you've seen before. little squirrel is the reserves I promised are in the system. And a needs assessment will use the values of all of these resources that are currently active today or under construction. An adequacy assessment will use your forecasted resources in a future year to then test adequacy. So think of adequacy assessment is when you know you have a strategy, and needs assessment is you need to plan for the strategy. You use the results of the needs assessment to guide resource decisions. I mentioned before, it's important to capture uncertainty. We're just going to dive through this. You can just see that if you test one case that will likely have shortfalls, you would think the system is always inadequate. But when you test more and more correlations, you end up testing the full spectrum of probabilistic uncertainty. This is what needs assessment and adequacy assessments are all about from a Monte Carlo perspective. It's the probabilistic approach to making sure that you're, we talked about the climate risk, their policy risks. Here specifically, you're looking at the key generation and demand uncertainties, and you want to make sure that you're covering your distribution. So for us, as an example, extreme weather, whether heat or cold, is in fact in the distributional data for our hydro and loads. So again, it's just saying it's how you capture them. There's two ways to include your criteria. This is a really important question because it depends on your on the tools that you use. You could use it as a constraint in the model. There are some adequacy models that solve for specific metrics. And so, for example, you could have a simulation that would satisfy your loss of load expectation. In that case, the solution already satisfied your criteria. For those of you who follow Genesis, that is not what we do. It is a post-processing of the simulated shortfall record. We talked about the many iterations. We create a shortfall record, and then we do statistical analyses to the tools. These are both valid. If your model has a way to incorporate adequacy as a constraint, you could do that. Genesis, our production cost model, has lots of constraints. Adequacy is not one of them. And so that we do capture reserves, don't worry. But the idea is that our adequacy perspective is post-processing, and it is not a constraint in the model. There are great models that do have it as a constraint. This is just saying that two ways exist. The tools that you have will influence how you handle your criteria, as just mentioned. Shortly, for simulations, you have N number of studies, you have the hourly output, you create your statistics, whether it's average and tail end or as your heart desires, and then you determine, is it adequate or not? Or if it's a needs assessment, you say, what are the needs for the future? Expected case, this is a theoretical, this is just an example from a previous study. You can see that the loss of load events metrics are 1.64 and 1.3. If your threshold was 0.1, inadequate. The way that tail end metrics work, again, it's a similar duration curve we saw before. It goes from the maximum to the smallest. You're going to have the VAR value. In this case, it's 27 hours and 3 hours. If your threshold, in our case, 8 hours, if the VAR value is above the threshold, you would consider inadequate. If it is below the threshold, it would be adequate. So this is just an example of once you go through the simulation, you get your shortfall records, you then ask the question, is the metric at, above, or below the threshold? And from a multiple metric perspective, you want to satisfy them all. It's not if one is yes, then the others. It's not that one is not satisfied that we're still adequate. All need to be satisfied. We're close to the end, I promise. The outcome of these assessments, when you're doing an adequacy assessment, it's whether or not you are adequate. If you are doing a needs assessment, it's quantifying, this is a longer one, you quantify the capacity and the energy needed to satisfy your criteria, and you translate those to, we call it adequacy reserve margins, you can call it planning reserve margins, but think of it as the percent above load, and this is the important link to the portfolio expansion model. Again, we'll talk about it in other sessions. This is where you translate your metrics to your planning reserve margins, and that too is pretty unique. Each utility can translate it in a little different ways. ELCCs do strike back. I know everybody has their favorite movie in the franchise. We don't have to argue about it. But who doesn't like Hoth? And it's important to understand that the signal to your capacity expansion model is very important. It makes sure that you don't underbuild or overbuild, and from a planner's perspective, it makes sure that you don't iterate 100, as many times as possible. If you get it right the first time, or if you get it as close to right, you have less iterations. The ELCCs, as mentioned, depending on the model, they need it as input. And so if your model has to have ELCCs as an input, the more nuanced your ELCCs are, the more appropriate and fine-tuned your results would be. We talked about it probabilistically is the preferred way, because then even your ELCC, which think of it as you add a resource, you see how it changed how it contributed to avoiding shortfalls, you can get an ELCC value. The math around it isn't the challenge, but probabilistically speaking is the preferred way. Otherwise, the deterministic block approach is another way to consider the overall signal. And depending on the model that you use, it's not that you have to calculate ELCCs. The key here is that there's a dynamic component to them. We talked about this in the beginning. They are sensitive to your portfolio mix, and they are sensitive to how much they have the law of diminishing returns. And so if you can dynamically calculate the ELCCs, or if the model can do it for you, your situation is a little different. But it is an important aspect. ELCCs are just one example, but from a portfolio perspective, it is very time consuming. And it could also be quite costly depending how if your runs are costly to do. And so ELCCs can come back at the end of a needs assessment if you use the adequacy results to derive them. Our final step, I mentioned this, that the needs assessment is both to feed into your scenario analysis and your portfolio expansion. You also need to test the strategy. Again, it's just convenient to use the power plan flow because it's very similar to IRPs. You don't want to just take the model results and say, we're done. You then test it through your adequacy model. There are some models that do both capacity expansion and adequacy. We do not. We have a separate adequacy model and a separate capacity expansion model. And so for us, it's more of a, there is that physical step we need to do, but depending on the tools that you have, it could already be embedded in it. But the takeaway is that you validate your adequacy afterwards. I promise suggested readings. These are, you have the slides. These are all hyperlinked. For those interested in the council's criteria, that's the top left. I do want to give a shout out to IEEE PES, really nice tutorial walking you different perspectives of metrics and considerations, really nice slides. ESIG in the middle, they've done, a few of my colleagues, we worked with them and others around the nation to really focus on new resource criteria and transitioning power systems. And so there's really nice examples from all around the US, not just our region. So I do want to say that's a really nice report, just to see what is happening in the US. And then I promised NERC really well-detailed description of the metrics, but I believe there is an update for some of these. So stay tuned on that. But I know I rushed through the second part, but we are good from my end and happy to take questions if there's time.
Yeah, let's take a few questions. I think the priorities, I think the open discussion, we kind of covered some of the things from a PNUCC perspective we wanted to highlight. We can find other channels and continue priorities into the start of 2026. So if there are questions, I think it would be a good time to get them. I also just put a short link survey for some feedback. You don't have to answer it now, but probably soon after this would be helpful while it's fresh, because we want to know how to kind of work on part 2. So hope this can help us get some guidance from you all.
I can bring back the slides if we need them. I can also open my camera now.
Well, I think for me, I'm going to share one thing. In the questions I asked, is any of this new information, and I feel like the dynamic reserves, putting that into the model feels new, and it's a topic I'm interested in. I also, yeah, so that's one thing. And you mentioned there's some great models that actually put adequacy in as a constraint. What are some of those great models?
So that is a great question, and so I do justice to not name one over the other that I could be wrong. I think Elizabeth, if you have, or both of you are looking at this, I think we have a one future session is going to talk about models. Is that correct?
Yes, that's the hope.
So
That's
I will defer to that one, but there's a few models out there. There are utilities that make their own, and there's, again, I mentioned some consulting and some commercial products. And so yeah, I suggest that's a great question, but let's make sure we give a holistic response to that one with more time to summarize other models.
okay. Sounds good. Then if somebody has a real specific question, a need to know about this, I can follow up directly with you, though, for some concepts on this.
Ben?
My question is about import limits. It feels like as a Pacific Northwest region in the reliability assessments, we seem to knowingly be relying on imports as a region. So when you think about that and reliability modeling, I imagine that's kind of like a hot topic. Are there like standard practices or maybe this is a NERC question. Are there regional assumptions that are considered best practices? At what point does a a region relying on other regions for reliability become a problem? But Dora, I think the council chose a more conservative number. Let's say, the spectrum of what you could have chosen, it was like 2 gigawatts or something. I can't recall the exact number. Was
No,
that?
so it's a great question. I can give the short version and then NERC or anybody else.
Yeah.
I think it's one of the key questions to ask. And in fact, when we did the survey, we asked individual utilities, what is your reliance? If you need something from the market, what's your limit? And can you offer something when you're short? And at least from an adequacy perspective, we know that there are some who would say, I want zero reliance on the market. And some say, no, actually want to do more. And you're right. The 2,500 the council uses in winter, the last winter storm example, region imported a lot more than that. There is physical transfer capacity available. I mean, assuming it's not, filled, but there is more transfer capacity than 2,500. The question is, that's right. That's a great example of what we would call the higher market purchases to satisfy adequacy event. It'd be interesting if we have a longer discussion on what the region wants to protect against, both outside and internally from protect against sounds a little aggressive, but to what market reliance to have with its neighbors. I think if all neighboring utilities agree on it, it'll look a little different if each utility has its own assumptions in a time of emergency.
See, Amanda's hand is up. I'm curious to hear
Is
your
there?
thoughts.
Yeah, I was just going to say, so this is Amanda Sargent with WEC, the Western Electric Coordinating Council, and we do the whole Western interconnection modeling so that we can really look at what the energy availability is. One of the things I really like that was touched on in the presentation was the difference between assessing reliability versus like economic, cost-effective capacity expansion type modeling, where an ELCC might make more sense. I can say through some of our surveying, specifically in the Northwest, we are seeing folks move from what they thought would be available, like what the market availability was going to be in past years. Several balancing areas have moved to zero and are not expecting anything, especially during peak hours or the net peak risk hours. And we're seeing that in other places. The other thing I'd highlight is NERC has had an effort here across North America to do more wide area energy assessments so that we can we can be looking at some of those and making sure we're not over relying on market availability during these wide area extreme events that we're seeing more and more of.
If I could just add a short sentence, and I think it was a related question to same as the gas pricing complexity. As the region, because we don't fully know what's happening in WEC, it's another limit from a modeling perspective and an assumption is because we don't know what's out there, let's put a more conservative limit. So again, this is a really good example of we need to know how to handle our unknowns. And so just one way of adding it is conservative. Green?
And I heard a topic around large weather events that cover massive geographic areas being a new thing. And so if we're seeing more of those, then that shift towards balancing authorities having fewer imports that they allow, that might be a mitigation against large geographic weather events. Is that okay? I'm understanding that correctly. All right, sorry. Go ahead, Breen.
Okay, hi, can you hear me? Okay,
Yes.
great. Sorry, I'm having weird troubles with like Teams and Outlook this morning. But thanks, that was a great presentation, Dora. I had a couple of questions that I don't know if there's not time to go into, that's okay. But one was you showed like a nice example of I think hydro, weather, and load conditions that you test, and you want to be within that like cube to test all the combinations, but those all seem like they're driven by like the overarching weather conditions. So I would expect there to be some correlation between all three of those, and so maybe exploring that entire cube isn't necessary. I was wondering if the council has thought about that or has any advice. And then the other one real quick, which I think I've asked about before, but you mentioned the council used the VAR 90 something, 95. But I still ponder from time to time, like whether using CVAR would be better, especially in terms of financial planning, or like, I guess, so I'm curious to hear more about the council's reasoning on choosing VAR over CVAR, because it seems like if that very most extreme event that you're not necessarily tracking with the VAR metric is just catastrophic, then at least from a financial perspective, it seems like you want to kind of mitigate that, but maybe that's outside of the scope of the council studies. So wondering if you can comment on those. Thanks.
Two great questions. The first one with the cube, so specifically the way that the data that we use for temperature and stream flows is from the RMJOC. So I do not remember the acronym, but it's the Joint River RMJOC. It's the joint collaboration with BPA, the Corps, I think the Bureau, and two universities. But they looked at 19 different climate change downscaling models for 30 years into the future for each one of them. And so you're right that the hydro and load signal that we're seeing is derived from the same daily model. And so we ended up using 3 climate models, different downscaling methods. And so our data is correlated in this case. Now, specifically, the way that we further do it is we have temperature sensitive variations across them. And so when we test an operating year in Genesis, it's looking at all of these different, 30 years within each climate condition. It's the temperature sensitivity of them. And so, yes, they are correlated in that case. Your second question, and maybe I misspoke when I explained something, the CVAR and VAR that we use is not financial. It's the CVAR, it's VAR for duration, magnitude, 2 magnitudes. It's duration and then greatest peak hour, and then annual unserved energy. The reason we ended up going with VAR followed our, because at first we were thinking CVAR, and then we were thinking, we were going back and forth with the advisory committee. Shout out to everybody who supports us. It's not the right word. Who participates and engages with us on our advisory committees. We always appreciate it. We made the decision that because we're not trying to protect against the largest events, what I know is a little difficult to say, but because there's a threshold that we are putting a limit on, trying to protect anything above it might further shift the risk to a place that we are not trying to protect against. Financially, I think you're right. So there's a different financial consideration that is not part of the adequacy metric. I see Dan, actually, great colleague, might pitch in here and either clarify something I said or say it better. Dan, do you want to follow up?
Oh, thanks, Dor. One reason that the VAR is used is that it directly relates to what Dor talked about. Has to do with your available emergency measures. That VAR is set to equal to your emergency measures for the maximum. I think Dor you can elaborate more on that, please. Thanks. So that's why CVAR wasn't used, because of the emergency measures purpose. Thank you.
I know that's a great reminder from Dan, and just taking it a step deeper, the way that we decided to use the thresholds were derived from the emergency measures. So how much is out there and how often we want to protect against them. And so a CVAR value would now mean average emergency measures, which are a little different from a specific emergency measure. So it goes back to the line in the sand versus fuzzy line in the sand. Might not be the best answer, and utilities you could have a different perspective, and it just depending on how you define the risk that you're trying to protect against.
Yeah, that makes a lot of sense. Thank you. Yeah, I think I missed the connection between the emergency measures also, so that really helps. Thanks.
Well, I think we have to wrap it up, but so I'm going to pass to Ben to help close out the meeting.
Yeah, thank you, Dor. It's a big presentation. There's a lot to go through, and I love the references, by the way, the Catan and the Empire Strikes Back. So thank you.